Hello, I am Professor Stephen Abbott. I'm an independent scientist who has worked for more than 30 years in industry while retaining strong university links after my PhD in chemistry from Oxford and Harvard. I troubleshoot, I write apps and I write books. My passion can be summed up in the phrase science-based formulation. I try to find the best possible scientific tools so that myself and others can formulate more effectively. In this video, I want to show how a rather simple but powerful idea can help formulators across all the areas covered by Special Chem, such as plastics, adhesives, cosmetics, inks and coatings. The idea is to take control over solubility and compatibility issues through a set of parameters from which we can readily calculate how like or unlike two components might be. Of course, you can just say these two are hydrophobic, so they are like each other, or these two are both polar, but these words are vague and you can't do much with them. Instead, I want to be able to say these two are separated by a solubility distance of 1, which is small, so they will be compatible, whereas those two are separated by a distance of 8, which is large, so they will be incompatible. Formulating with meaningful numbers allows us to compare and contrast, to optimize, to make smart judgments, to rank component by distance, to do science-based formulation. So what tool allows us to do this for solvents, cosmetics, adhesives, plasticizers, particles, inks and coatings? It is called HSP, Hansen Solubility Parameters, and it is based on just 3 numbers. Don't be put off by the word solubility. HSP are equally applicable to compatibility and dispersibility issues. A helpful trick is to think of them as similarity parameters. From now on, I will just use the word solubility. You can feel free to change it to similarity or compatibility if that makes more sense for your formulations. And the great news is that they are easy to use, and Special Chem is providing a large set of HSP data and formulation tools to help you use them. Let's now look at what they are. Solvents like heptane or polymers like polyethylene are held together by just one force, dispersion or van der Waals. So if we are to describe solubility, we must include a parameter, dd, to cover dispersion. We will talk about the numerical values shortly. Solvents like acetonitrile or polymers like polyacrylonitrile have a strong polar component which holds them together. So if we are to describe solubility, we must include a parameter, dp, to cover polar forces. And then, of course, alcohols and polymers like polyvinyl alcohol show strong hydrogen bonding attractions, so we need DH to cover hydrogen bonding. The HSP system works by assigning these 3 parameters to any solvent, polymer, particle that you want to use. The convention is to list them like this, in square brackets, DD, DP and DH. One of the many great things about HSP is that the values of the 3 parameters make intuitive sense to formulators. Let's look at the values of a few solvents and polymers. Obviously heptane is all DD and polyethylene is very similar, with a higher DD because dispersion forces are generally stronger in polymers. Benzene has more DD than heptane because of the aromatic electrons, and polystyrene has more DD than polyethylene. Acetonitrile has plenty of DD, indeed everything has plenty. It's what holds the world together. But it has very large dp, which is not surprising given its high dipole moment. In fact, you can get a good estimate of dp simply from knowing the dipole moment. Of course, it has some dh. You can form moderately strong hydrogen bonds with acetonitrile. The values for polyacrylonitrile make sense too. Ethanol has plenty of dd and dp. It has a significant dipole moment, but it excels in DH because of its hydrogen bonding capabilities. For the polymer EVOH, we see a range of values as the OH content is increased, with the typical EVOH being 17, 8, 19. So how do we use these HSP values to measure the distance, the likeness or unlikeness, between molecules? It's simple. We just calculate the distance, a sort of 3D Pythagoras calculation, based on the sum of the squares of the differences between each component. Let's do this one step at a time. If we have 16, 5, 6 and 18, 12, 3, then we square 16 minus 8, and that gives 4. 5 minus 12 squared equals 49, and 6 minus 3 squared equals 9. Together that makes 62. Take the square root and we have our distance equals 7.9. Actually, for various reasons, we amplify the DD difference by a factor of 4, so the HSP distance is 8.6. And experience has shown that in general, distances less than 4 imply compatibility, distances greater than 8 imply incompatibility, with a grey area in between. Let's use this idea of calculating distances for 4 different formulation challenges. I have a solvent, 1768, that I want to replace with a greener solvent. Which should I use? From a list of green solvents, I calculate the distances, sort them from low to high, and immediately have some good ideas. The table is data obtained from a software package called HSPIP. You can do a similar job with just an Excel spreadsheet. As you can see, the solvent that is the closest match and is nicely green is anisole. I want to add a new active to my skin formulation. It's HSPR1768. We don't need a computer to tell us that it won't be compatible with, say, isopropyl myristate at 1622. So what excipients should I add to increase compatibility? Again, take a list of your favourite excipients and sort them by distance. Now we see that methane-diol is the closest match. I want to get a nanoparticle with HSP1645 into a polymer. Which common polymer is the closest match? Here's my list of polymers. Oh yes, it's obvious that polysulfone is closest. And I want to find a greener plasticizer for my polymer with HSP1748. From a small list, I can find that acetyl triethyl citrate is best, and that we don't need to be tempted by the non-green phthalates because they are likely to be incompatible. With a larger list, and Special Chem are providing one, some better ideas might emerge. Where do these HSP values come from? For common solvents and polymers, they are well known and readily available, and Special Chem are providing many values as a service. For many molecules, it is possible to use the so-called YMB method within the HSPIP software package to estimate the values from their SMILES strings. Special Chem has used this technique for its first generation of HSP values across its large database. But for many ingredients, you have to measure the HSP. I'll describe the classic method. Other methods, for example using inverse gas chromatography, are available. We take, say, 20 test tubes and we put a small sample of our polymer, particle or active ingredient into each tube. We then put a different solvent in each tube, give them a shake and use our judgment to say whether the sample is happy or unhappy in each solvent. Why an unscientific word such as happy? Because a good solvent might dissolve one polymer, it might swell another if it's cross-linked, might provide very good suspension for a pigment or particle, or might dissolve just enough of a tricky API to be useful. There is no single word to describe all these good outcomes, so the word happy, as judged by you as the expert in that system, is appropriate. With these judgments, we can create a sphere. All the good solvents should be inside that sphere, i.e. the HSP distance is smaller than the radius, and all the bad solvents are outside that sphere, i.e. the HSP distance is larger than the radius. The center of that sphere is the HSP of the sample. Although you can do this in your lab, you can also outsource the process to experienced teams such as VLCI, one of the science-based formulation group, who have a wide experience of doing such measurements and providing validated answers. Let's pause and review. We've just said that via 3 numbers, easily estimated or measured, we can readily optimize our formulations by controlling solubility, or, if necessary, insolubility, through a simple distance calculation between pairs of numbers. This raises some questions. First question, is there any scientific justification for this? Yes, plenty. The idea builds on basic lattice solution and corresponding state theories from giants such as Hildebrand, Flory and Huggins, and has been in continual use for more than 50 years. Second question, does it work? It is a simple theory and so cannot possibly be entirely accurate. But all over the globe, academics and industrialists use HSP on a routine basis for getting close to an optimum formula. Third question, are there alternatives? Yes and no. In my view, the finest solubility theory around is Cosmo-RS, which I use alongside HSP. But it is a big, expensive, complex technique best suited for pure solutes and pure solvents, not the tough world of formulation science. Other techniques, such as Abraham, Camlet-Taft, Unifac, are wonderful in specific domains. I've personally used each of them, but they simply don't have the wide, real-world applicability shown by HSP. So far, I've mentioned simple cases of one component in another component. But in our formulation world, we seldom have the luxury of just two components. This is where HSP are especially powerful, and I want to give a specific example developed and demonstrated by VLCI. Take some red nail polish, which is not, of course, a single polymer or pigment. Coat it onto a large number of microscope slides and dry them. Now put those slides into 20 solvents and see which are good, the polish falls off the slide, and which are bad, the polish is untouched. Then do the usual sphere trick and you get the HSP of red polish as a whole formulation. This already shows that HSP is a real-world technique. But that's not the best part. It turns out that neither benzyl alcohol nor benzyl benzoate dissolve this polish. But if you take their HSP values and make a 50-50 average, you find that that blend is not a bad match. Each compensates for a defect, in HSP terms, in the other. Make up that blend, dip in the slide, and yes, it dissolves the polish. This tells us of two general HSP principles. First, the HSP of a mix is simply the volume-weighted average of the HSP of the individual components. This means that we can get the HSP of, say, a cosmetic formulation, which itself is based on components that are mixtures. Second, when we need to make a solvent replacement, we are not restricted to single solvents. We can rationally fine-tune a blend to get not only the solubility, but also the volatility, cost, safety, odor, or all the other properties that are part of our formulation specification. Let me give you an example. I want to replace the nasty solvent X with something greener and safer. But my list of green chemicals shows no obvious match with a similar volatility, which we can assume to be an important extra parameter. Okay, let's find some green solvents with similar volatility and find a blend with suitable solubility. Although I'm not showing it live, I will do it in the advanced video, using the principles described earlier, this is a straightforward task. Try doing that with intuition or hydrophilic hydrophobic. Let's think of some other complex situations. I have a polymer in a coating or ink, and I want it to stick to the surface onto which I'm coating it. We have multiple issues. First, the polymer has to be soluble in the solvent system. We already know how to do that via a short HSP distance. But next, we want the solvent to give a little bite into the surface. Too little bite and there will be no chance for good adhesion. Too much bite and the surface is destroyed. So the solvent has to be at an intermediate distance from the surface polymer. Finally, the two polymers need to be compatible enough so that they will intermingle and entangle to give strong adhesion. In general, this is a tricky juggling act, but with HSP we can rationally tune the conflicting requirements, for example, adding just the right amount of a co-solvent to get the right amount of bite while keeping the original polymer happy. This sort of three-way optimization is much harder without the help of a rational formulation tool. In the image, a good and bad solvent have been chosen as a blend, and the cyan dot shows what is probably the optimum blend for our purposes. Again, this will be shown in the advanced video. Now let's find the right dispersant for a pigment. The head of the dispersant molecule has to love the pigment, and the tail has to love the medium. If the medium is complex, that's not a problem because we can calculate its HSP via the blending formula. But there's a potential problem. Suppose the medium really loves the tail. There's a danger that it will entice the dispersant away from the pigment. So smart formulators tune the HSP of the system to get the right balance. This, incidentally, is not some intellectual nicety. Charles Hanson used this principle decades ago when he worked for PPG Paints, and a recent paper on formulating complex ceramics confirmed that exactly the same principle was necessary to get a great result. And what about cosmetics? Some of you know that for years I have said that skin has an HSP value of around 1788. So if you want an active to go into the skin, you need to formulate so that, first, the active is soluble in the excipient blend, and second, that blend is nicely compatible with the skin to encourage the active to enter. Those who are serious formulators, especially from pharma, use HSP for such optimization via a package I co-wrote called Formulating for Efficacy. This is now used around the world by serious formulators who find the approach works very well. Even without investing in a standalone formulation package, you can still do a lot to guide your formulations rationally via HSP. I hope I've shown a few things. First, that HSP are simple and intuitive. Second, that they have respectable scientific credentials and a long history of use across many formulation domains. Third, that we can readily calculate how like or unlike two components are and therefore make rational formulation choices. Fourth, that we can estimate HSP values for many molecules and measure many others by ourselves or via expert service providers such as VLCI. Fifth, that we can handle complex mixtures and use the HSP mixing rule to tune our properties. Sixth, that we can handle complex formulation trade-offs. That's why the Science-Based Formulation Group have committed so much time and effort on HSP as our first big formulation principle, with lots of data and resources from day one and much more to come. And finally, a message to our sponsors. Special Chem would not exist without the active cooperation of the companies that provide us with the raw materials needed for our formulations. Many of these suppliers do not currently know the HSP of their products. The message is, your customers need those values. In the short term, we can provide estimated values for relatively pure chemicals, but many products you supply are sophisticated blends or contain confidential materials. Help us all by getting into the habit of providing your HSP values. In the short term, you will have a competitive advantage over those who don't. In the long term, if you don't, then your competitors will win. You already do a lot for your customers. By providing the HSP values, you will be showing your commitment to science-based formulation, which is the direction in which we must all travel. If you would like to know more about formulating with HSP, the next video brings the ideas in this video to life, as I show you, using live software, how one might tackle many complex formulation issues with HSP.